Dear professors, today I'm going to talk about the linear programming problem, and let's start about talking the general linear programming problem. The general linear programming problem is actually says a linear programming problem is a minimization or maximization of a linear objective function with n real valued variables, and what is the value of the objective function if a particular set of the values for variables that is called the objective value, and if particular set of values for variables satisfy all the constraints, that means that is called the feasible solution. And a feasible solution that has the minimum or the maximum objective value, linear objective value of the objective function, that is called the optimal solution. And we also have to notice that optimal solution must satisfy all m constraints. And it is not allowed, the general linear programming is not allowed to have the strict inequalities. And how do we find the optimal solution? we get an algorithm which is called a simplex, and simplex is actually requires us to do some operations based on the slack form, and before that we need to know what is the standard form. Our linear programming, the standard form requires us we need to it is a maximization of a linear function, and also it is n non-negative variables, and also it is satisfy m inequalities. Yeah, so it expressed like
kvinders rettigheder og normer og standarder går i den sene Tysklandsperiode. Og jeg har ikke nogen, hvad hedder det, afstand på, fordi der er ikke nogen afstand af mine kilder. Jeg havde også ikke noget problem. Jeg havde vide sådan, nu er jeg sådan det så, fordi du ved, fra studiet, og nogen sådan, hvad man sætter årstal på, jeg var sådan, ej, der var jeg ikke. Jamen, vi kan jo gøre det. Altså, hvis jeg kunne skifte de der årstal, det var sådan, fordi det er sådan overflydende emner.
Yeah, this is the expression of the general of the standard form linear programming problem. And then we how do we convert it is that we according to this expression, if there is a problem, it is a minimization, we just multiply with -1 to get it to be a maximization problem. And if there is a variable that we solve a non-negative constraint, what we do is just we replace it by using a pair of the non-negative variables. That means if x2 is non-negative, is without a non-negative constraint, we just replace x2 by x2 minus x3, and the constraint, we add two constraints, x2 and x3 is non-negative, are non-negative. And we also, if there is equalities in our general linear programming problem, we just opposite this equality to be greater than and less than, and for the greater and or less or equal than this equation, we just turn around by multiplying a -1. And yeah, that's all. Yeah, and then we have slack form, linear programming slack form. And for the slack form, we just insert a slack variable to make all the constraint, all the inequalities to be equalities. And how do we express it with that? We just, yeah, it's actually, we just add xi plus a, and here we just plus a and b. Yeah, and this is a slack form. Yeah, and then we have slack form. Then we actually know that the solution of the slack form is actually the same with the solution from the standard form. And we set the objective function equals to z here, and the slack variables over there, and then we call the left hand side is equals to the left hand side is called non-basis basis, and every variable here, slack variable here, is called the basic variable, and here the right hand side is called, the variables are called the non-basic variables. And in the first step we just set all these basic variables to be 0, so that means our basic solution will then we get our basic solution. The z will be 0, and the basic solution, the basic variables are maybe not 0, but the non-basic variables will be 0. And but we need to know that the basic solution is not does not have to be the feasible solution. Then we have our simplex algorithm. Our simplex algorithm, there is a very core idea that is pivoting. So actually the steps of the pivoting is that we choose a non-basic variable with the maximum positive coefficient and the smallest indexes, and then we find that the binding basic variables, and we let the binding variable, basic variable, leaving the basis, entering the non-basis, and the non-basic variable leaving the non-basis and entering the basis, and then we compute the new objective function value, yeah. And this is actually the simplex pivoting do. And the simplex will terminate at LP is unbounded, or there is no there is no positive coefficient for every variable, non-basic variables in our objective function. And we also have some cases like, which is called the degeneracy. It is actually means that it is possible that our objective value can appear twice. That is the degeneracy. And we also have another case which is called cycling. It actually means even if it means that it is possible that our objective function one solution might appear more than once, and even though that we specify, we choose the maximum coefficient, positive coefficient, and the smallest, it still happen, have the probability to happen. And let's talk about the duality. The next topic I would like to talk about is duality. The duality is actually the method we can verify our optimal solution, whether it is correct or not. The duality means and if we would like to every linear programming in the standard form have the associated duality. And how do we get that? We have two different ways. The first way is that we use a linear combination of the with some multipliers. So here is the standard form, and then we multiply with y and both sides, and they should satisfy. And we just make the standard form, change the standard form into the problem in respect to y instead of x. And because we would like to find we show more interest to the maximum of the objective value, so we would like to find the upper bound of that value. So we would like to minimize our duality objective function. So we could rewrite our duality problem like minimize of the BIYI, and from I equals to 1 to m, and this is such that the sum of the from I to 1 to m, and AIJ less or equal than the CJ from J equals to 1 to m, and here is YI greater or less or equal to the 0, and I from equals to 1 to n. This is corresponding duality of the associated standard form of the linear programming problem. Yeah, and we have a theorem that if we assume that x star and y star is both of them are optimal solution to their problems, then they are actually the minimum of the maximum, the minimum of the dual equals to the maximum of the standard form linear programming problem. How do we prove it? We actually do the transformation here. I would like to do the proof here. J from 1 to n, Cj, xj. Yeah, we can extend it to be from dual. We can replace this Cj to be like this, and so we extend it like this, and then because it's just a simply reordering of the terms, we just put this inside and this outside, so it will be in this one. Then we have we from the primal we can know it's actually the BI, so it holds. And the other way to get the corresponding duality is that we just can think of this question by transpose over the variables coefficients here, but I will not mention it over there. Yeah, and that's all. There's